почему-то конкретно без домашки с лекциями хотя бы не должны быть, потому что мы уже такой курс читали, ничего не поменялось. Ну, случилось, как бы, я думаю, не сильно страшно, будет просто больше времени, да. Заранее знаете, когда домашки, может, сегодня уже вопросы по авторизации задать. Соответственно, сегодня вам новую домашку выдавать не будут, но Олег придет, если у вас есть какие-то вопросы по текущим домашкам, он ответит, как бы, кто-нибудь расскажет. Какие-то вопросы есть? Какие-то в целом вопросы по предыдущим лекциям? По машинному обучению? Окей. Let's start. So today, this theme is clustering, and this is actually one of my favorite lectures because you can actually see what is happening when you cluster different algorithms, and I like it when the next algorithm answers some problem with the previous algorithm, and you can clearly see the evolution of clustering algorithms here. However, well, the task itself is quite ambiguous, and well, why do we cluster? No one knows, right? Well, here are some examples of why we can cluster. The first one is information extraction, right? You can get some insight from the data, and say, okay, there are 5 clusters, for example, of people. Does it mean there is only 5 types of people? Maybe, maybe this. Creating hierarchy of objects, that could be useful well, if you do hierarchical clustering, which one of the ways of hierarchical clustering we will discuss. And to know, maybe you can use it, for example, in some tree algorithm. You can create hierarchy and then search in those clusters. Data simplification, well, here we go sort of in parallel with prototype selection, right? So let's say you have 1 billion points, but you can have 1 million clusters, right? And then just select centroid for those clusters, and you have 1 million points now. Data compression, sort of the same. Anomaly detection, right? There are some algorithms that leave points behind. So, for example, you can have points, you cluster them, and you have 5 clusters, and some other points that do not belong to any cluster. And those are anomalies. That's sort of important as well. And feature generation. Well, this is, in my personal opinion, is the most important reason to cluster. So when you have some feature space that is strangely organized, and your algorithms need help to try and revise the geometry, or if you have a very, very high dimensional feature space, well, then you again can cluster with some tricky algorithms, and then you arrive at a new feature, which is the number of clusters, of course, with one-hot encoding, because we don't want to introduce new distance, a new order. And well, this is how clustering is most often used. Well, first and the last one, right? The first one is information extraction, which is you can show your clients, that pays you money, look, clusters. Oh, here's more money. I like clusters. Everybody loves clusters because pretty pictures. It's bullshit, but still useful. Clustering is an example of unsupervised machine learning. So there's no specific task, right? We don't have a metric per se. We can introduce some metrics, and we'll talk about clustering metrics. And no specific quality criterion, which is, again, sort of hard. Like, how do we know after we cluster that we did a good job, right? How do we know that clustering was good? No, we don't know. We'll discuss some ways, but they're all superficial in some way. The thing, okay, the first algorithm is the simplest one and most often used is k-means. And here, we get confusion every time because we just discussed another k algorithm, right? K-n-n, k nearest neighbors, and this is k-means. And this is, I guess, the most confused terminology on interviews and stuff like that. If you ask a person about k-means, they start telling you about KNN and so don't confuse them, because, well, especially during the interviews. K-means clusters through centroids, or centers in this case. So every cluster is defined by its centroid. So here's the centroid, right? And say, okay, the points that have that centroid as the closest centroid belong to that cluster. So here's the orange cluster. All of those points, the closest center is this one. Right? Well, this separates the whole space into what we call Voronoi diagrams. Maybe you heard of that. Well, this picture basically. It's called Voronoi diagrams. We have points, and they're separated from middle perpendiculars. And well, okay, let's say we have 10 centers and they're randomly distributed. They will give us 10 randomly distributed clusters, right? Just 10 random clusters. And well, this is a sort of bane of k-means algorithm, because whatever you do, it will still output the number of clusters that you tell it to output. So it's hard to extract some information from that, and it's a bad way to extract any new information. It's a good way to generate features, right? Because, well, it's still some localization, still you can extract some information about geometry, but, I mean, the number of clusters is predetermined, right? It's predefined. You say, okay, give me 10 clusters, and it will always give you 10 clusters, whether or not there are actually 10 clusters in the data, right? So, but if we just output the random clusters, well, we didn't do anything, there is no algorithm, right? What algorithm tries to do is to minimize variance in this form. So try to minimize the sum of distances to the nearest centroids. Right? And it's an iterative algorithm. We start from random. Right? Here we can sort of show. I have a red center. I have a red. I do have a red. Here it is. I have a green and a blue center. And the squares are points. So here we start from random centers, and then we assign points to clusters, right? So here, the red point, this point is red because the closest center is red. These points are green because the closest is green, and these are blue. Right? Yeah. Do you have a question?
No.
What? I don't know. Okay. The next step is we move the center to the center of mass of those points. And we assume that all masses are the same. Right? So this has a mass of 1, this has a mass of 1, they all have a mass of 1. Right? And we move to the center. So here is what is it? Well, here is just 1 point, so the center of mass is this point, right? So we move it here, and this shifts a little bit down, and this shifts a little bit up here. And we do the same thing again. We reassign points, right? And we again shift centers. And we do it until convergence, which actually happens pretty fast. K means doesn't take a lot of time. It's usually done in 10 iterations, no more. Any questions about the algorithm? Yes.
We should choose
Random.
points.
Random points. No, well, we'll talk about that, yes. The vanilla algorithm just chooses a random point in space, in feature space. But you can, of course, choose some random points from your data. We'll talk about that.
И вообще количество тоже различное. Ну, все равно.
No, the number is predefined. So you as a user, you define the number of clusters. Right? And that's like the main problem with that algorithm is that yes, it will give you the number of clusters that you ask for. But there is no information contained in that. So for example, this is, I will avoid any company names, but one company, I was evaluating their work, and they said, okay, to evaluate some economic statistic, we clustered all people into 10 clusters with k-means. And now we have 10 groups of people, and that means that there are 10 groups of people. And we can now look at those groups and make some insight from them. Well, I said, okay, but why 10? Well, there are 10 groups. K-means says there are 10 groups of people. No, you told K-means that there are 10 groups of people. Why 10? Why not 8? Why not 11? Yeah, well, their head of department was very, very angry with them. So don't do that, right? Don't extract information from an algorithm that you put into the algorithm yourself. So k-means is not a good way to extract things. Here's just a description of the algorithm. So we initialize clusters at random, assign data points to the closest center, and then reassign them to the center mass of each cluster, and repeat 2 and 3 until convergence, which happens pretty fast. Now, when you talk about like cluster geometry, you can see pretty fast, like if you have a nice picture, nice cluster pictures, you can see that there are many problems with k-means. One we already discussed is the choosing the correct number. What is the correct number? Sorry. So here, for example, we can see with our eyes, our human eyes, that there are 4 clusters here, right? Well, pretty obvious. But if we told k-means, in this case, for example, that there are just 2, it will select 2 clusters. Sorry if I know this. I'll try to stand at least somewhat still. So here, we have a green cluster and a red cluster. Because we told k-means that there are only 2, right? Even if we know the true number of clusters, we still have problems, right, with initialization and moving. So for example, here, we know that there are 4 clusters, and we initialized 4 centers at random. And then they start moving, right, and they start moving. So here's one step of k-means algorithm. So we have 4 clusters, 4 centers. These are all assigned to that one, to the closest. These points assigned to that one. And these are all assigned to yellow, right? And this point gets nothing, no point. So it stands still because, like, why? So now we have 3 clusters here. Like this is the end. So just basically 2 steps and it's done. So we have now 3 clusters instead of 4 because we initialized it wrong. Now, if we go from initializing with random point and feature space to a random point from a dataset, then it still stands, right? Because we can initialize 2 points in the same cluster. And it still be the same. So here, this is the final result. So there you'll have 2 clusters in one, and these 2 clusters are merged in one. So an algorithm that updates k-means to solve such a problem is an algorithm of a better centroids initialization, and it's called k-means plus. And we do it as such. First, again, we select the first one at random among points in the dataset. So select a random point from the dataset. Okay, this is the first center. Then we calculate the distance from every point to its nearest cluster, to its nearest center of the cluster. So now, at first we only have 1 center. Let me draw something. So here are points. We select some random point. Then we calculate distances from every other point to this point. Right? This is M. And then we choose the next point with a probability that is proportional to M squared. Okay. How do we do that? Any ideas? So for every point now, so we have a list of points. Right. This is center, and for every point we have M squared. It's 1, 2, so we have values. Now we need to choose one point, just one, with probability that is proportional to this. How do we do it?
Посчитать сумму квадратов и сделать с вероятностью m квадрат x1 делить на сумму квадратов.
Well, then we can choose several points, right?
Еще что-то.
Well, let's, okay. So let's calculate the sum. Which is always good. And you propose that we choose every point, or do not choose, with the probability of x1, for example, and the sum, right? Well, then we can choose more than one point, or less than one point, right? Because every one is a throw of a die, and 2 points may be chosen.
Or мы можем выбрать случайное число от там, одного до вот этой суммы и посмотреть, какое там по partial sum попало.
Yes. Do you understand? Or just reiterate. So we basically create an interval with an equivalent squared, and every point takes some subinterval here. So this is x1, x2, okay, which is m. This is m squared of x, right? And we choose one point of random somewhere, right? And this points us to good. We do that, and we select the next point. Let's say it's this one, right? And the further away the point from the center, the higher the probability of it being the next center, right? So then we recalculate m's, because m is the distance to the closest center. So these stay the same, and for this point, the m changes for this one. Right? So we try, at every step, we try to select the point which is the furthest one, well, not the furthest one, but further away than other points from already selected centers. Why do we not want to select the furthest one every time? Why do we do that probabilistically?
Ну, что будет ситуация, когда мы все центры подвинем в одну и ту же точку?
No, well, we cannot. Let's say we select one point at random.
Когда у нас есть одна точка очень-очень далеко в целом от кластера. И мы все будем двигать туда.
No, just one. So this will be the next one, and the next one will be the furthest away from those two. So somewhere here, right? And the next one will be first. So actually, in this way we marginalize our clusters, right? We start from the edge, which is not correct because this probably is an anomaly, right? If this is far away from everybody else, then this will just be one cluster, one point in this cluster, right? It's not a good idea. Okay, so we select k points in this manner, and then we launch the k-means, right? So this is not the final centers. This is just initial centers for k-means. Right, so the last step of k-means plus algorithm is k-means. So first we initialize, then we launch k-means. But still the problem persists, is we need k. Right? We need k, we need to find what is the number of clusters, and we predefine it. So it's already biased with our. For example, people love number 10, right? Or 5. Good number. So there are always 10 clusters and everything. It's just we love that number. And it's good. So next algorithm solves that problem. A problem of the predetermining number of clusters. And it's called mean shift. And so we're still dealing with means. We're still dealing with centroids. So we still determine a cluster by the centroid, and we still separate our space into Voronoi diagrams, but we do it with no predetermined amount of clusters. How do? Well, if there are n points, we start with n clusters. So every point is its own cluster. Right? So we start with mu's, which are centroids. Right. Let's hope this works. Okay. So this we start from mu's, which are axes. So we take every point and create and say that it is the center. Now we shift at every step. We shift, so we have index t and index I, which I is just number and t is this time step, right? So at every point we shift it to a center of mass. But now we have masses that are not equal. So what here is we have a center of mass of points, right? But now we have a mass to a point. So now this point xj has a mass RBF of xj minus mu. And RBF is this, it's Gaussian kernel. We already saw it when we talked about K, right? So this is distance and this is exponent, so it's Gaussian kernel. So the closer the point is to center, the higher its weight. What will it give us? Well, let's, you still know, right? Eraser? No. Okay. So let's say we have these two clusters, and we have a point mu here. Right? So if we just take a center of mass of these points, then it will shift here. Right? But now we have a mass, so the closer the points are to this point, the higher the mass. So these points have high mass, and these points have low mass. So now when we shift it to the most dense and close area. And this is the definition of new shift. It tries to shift centers to a close and dense area. Right? So every point now begins to shift. So we start this mu point. It will start shift here, and goes to the center of density, sort of. And we start moving here, and all those points, they shift here, and these points shift here, and this point shift here. So we repeat again until convergence, so there is no change in coordinates of centers, and so the shift is, there is no shift, we are in the center of mass, and then we merge close points, right? So you have many mu's here, many mu's here, many mu's here, and then you shift it. Okay, this is the center of cluster. Now you can determine what is the correct number. Any questions?
Some neighbors, no, как вы это дерево просто выбираем какой-то карты.
Well, it's usually chosen by radius,
Okay.
or, I mean, it can be all points. Right, because you still have mass which is decreasing, so it can be all points. Usually it's some radius. Or number of points. 10 nearest points. Well, 10 is low, 100. Yes?
How many clusters do we start with?
N. Well, every point is its own cluster. Yes. So when n is the number of points, then n clusters.
Да, mu и t это mu и tt, или как вам сказать, вот в RBF, где у нас mu t плюс первое, и t высчитывается, ну, в общем, там скобочка.
Там верхний индекс должен быть или нет?
Не, выше.
Well, sure, but it doesn't, well, we calculate it here.
Да.
Sure. Well, it doesn't matter. This is mu e t, yes, of course. But, I mean, we only have one mu. At one step, we only have one mu, right? This is the next one. So we don't actually care about indexes. This is just mu next, and this is mu current. Yeah, but I will correct it. Thank you.
How many sensors?
If they're close. But they will be, like, you will know, right? They're really, really close. They all come to sort of one center mass. You won't have to guess. Okay. Any questions? Just choose some.
Хорошо, что РБФ просто другого, и можно любой использовать.
Yep. You can use triangle as long as it's but like the traditional one. Well, there's uniform kernel, right? Uniform kernel, you're right. Mostly gaming. Okay. Now we solved the problem of number of clusters, I can show. We didn't solve every other problem of k-means. And the next problem is non-spherical cluster. So k-means like spherical clusters, right? Let's say we have these two clusters here. And even if we know that there are two clusters, and even if we initialize the centers properly, we'll still arrive at incorrect solution. Right? This is just how k-means work and how it separates the space. Well, this is a sort of made-up problem. Like clusters in real life don't look like that, almost never. In some, in some spaces that are specially created that encourage these types of clusters. For example, you want some, pull out some proteins in space, and you want like the properties to stay the same. And you actually have somewhat curved clusters, but not like that. Mostly clusters are globes, but even with blobby clusters, you still have problems. For example, here, well, there are three globes, and they're spherical, and there's no strange. But the problem is now different sizes, right? Like two small clusters and one big one. And if we do k-means again, if we do everything correctly, we know there are three clusters, and we cluster everything, still there will be those blue points and green points in the cluster. Again, because the center is here, what we're going to do, separation, like the separation line will be in the middle between two clusters. And the problem stays with mean shift as well, right? So with mean shift we solved the problem of number, but we didn't solve the problem of non-spherical or different sized clusters. How do we solve it? With next algorithm, which is one of the most commonly used one. And well, there are many clustering algorithms, right? We discussed it when we talked about prototype selection, right? Every paper this year that's talking about, wow, this is a cool new clustering algorithm. Yeah, sure, probably. But we mostly talk about what is often used, right? And dbScan is one of the most widely used. Density-based special clustering of applications with noise. And actually every word there means something. Well, they probably want the word scan in there, you know, the scientists and their acronyms, but still. The number is not predefined, right? But we have two new parameters. Actually three, but the important ones are two. And there's m and epsilon. Two new parameters. How does the number work? Well, we have m and epsilon, and we first find core samples. And we define a core sample. Core sample is a data point which has at least m other data points in its epsilon neighborhood. Right? You need AI, you know. Right. Okay. So we look at the point, look at this epsilon neighborhood, and we calculate the number of points. And if it has at least m points, then it's a core point, and we mark it as a core point. So first we go through all points in the data set, and we mark core points, or core samples. And then we merge, right? We take all the neighbors, so neighbors, if they are within epsilon, if two core samples are within epsilon, then we merge them into one cluster. So these big circles are core samples, and the little circles are not core samples. So these are all merged into one cluster, and then we add the neighbors as well. So if a point has a core sample as a neighbor, we assign it to its class. And some points are left out, right? The black points, they don't have a core sample as their neighbor. And they're not core samples by themselves as well. So this is why it's density based, because you need something dense, right? So there will be in an epsilon neighborhood m points. Spatial clustering, because you have space, or you want it S for scan, because dB can is not good sounding. And noise is, you have those black points that are noise. Right? You don't belong to any cluster. So you find anomalies already. Well, dB scan is a good algorithm. There's one huge problem with that algorithm. Two, M and epsilon. How do you know what is the correct M? How do you know what is the correct epsilon? And it's very, very, very sensitive to it. Like you change epsilon a little bit, and you arrive at a whole different number of clusters. Or you change M a little bit, and then the picture changes dramatically. And that's the problem. I mean, again, if you have a metric for your clustering or for your end algorithm that uses clustering, you can sort of do a search for optimal parameters. But the problem is here, it's not stable. What is, again, important is with k-means and mean shift, we needed a vector space, right? Because we needed to add vectors up and find center mass, so we need to know how to divide vectors, right? And with dB scan, we don't need it. We only need the distance, correct? Because we only need pairwise distance to find how many points is there in the neighborhood. So again, if you want to use something for strings, for DNAs, for proteins, right? Are there any bioinformatics here? Not yet? Oh, well. Two warriors of bioinformatics among useless people. Sorry. Joke. Okay. Here we do not need a vector space, just distance. Good. And the next one is an example of hierarchical clustering. It's called agglomerated clustering. Or not. No. Oh, yes. Yeah.
Правда, что у нас, когда точки проб становится, она становится epsilon?
No, there is no size to a point. This was just a visualization.
Как это два ядра можно видеть?
Let's connect them into a graph. So we don't join them and there is one point. No, we just say these are joined. We create an edge in a graph. Right? So let's say all points that are core, we put all core samples in our space, and then we connect points that are within epsilon, core points, core samples that are within epsilon with the edge, and then we select graph components, and those are clusters. Okay, agglomerated clustering. Again, a very popular algorithm. It does not solve the problem of a number of clusters because, well, it sort of solves it. Because it will give you output for any number of clusters. Right? So it will give you options for one cluster, two cluster, three cluster, or and up to n, which is every point is its own cluster. So it will give you options. But I mean, it still does not need a vector space, which is good. It only needs the distance defined. But how does it work? We go from bottom up. Every point is again its own cluster. And then we merge points. In the merged points, with a metric. Metric is a parameter, so we add this like a word metric. Word is a surname, I think. Average or maximum. So the draw, I can erase the super maximum.
А що вийшли строку?
Yeah.
Назад чекається мені, де назад?
Да.
О! Да, это по-моему. Yes. Thank you. В прошлый раз здесь была штука без пляжа. Это было очень интересно. То есть она доступ была. Окей. Points. Points and clusters. Points and clusters and points. So, okay. Let's say we already merged this cluster, and let's say this point is its own cluster for now in this cluster. Agglomerated clustering goes through all pairs. Right, so it's okay. These pairs, this, and calculates the metric. So either a word, which is a variance of joint cluster. So let's say we merge these two clusters. Let's say we merge these two clusters. What would be the variance? Right? The variance is distance to squared. Average, which is average distance between points and clusters. So it calculates all pairwise distances and average them. And the maximum is, well, we take the maximum distance so between two furthest points. So three main metrics. Right? Variance of new cluster, average distances between two clusters, and maximum distance. So we use one of the three, well, we choose one in the beginning, and we merge. So let's say, okay, we have 6 options, right? This, we calculate a metric and take the minimum. Always take the minimum, right? Let's say we take the maximum distance between points. Well, probably minimum here will be, I don't know, this one, right? So we merge these. And we do it until there is just one cluster with all points. We'll always end up at one cluster, correct? Because at every step we merge two clusters. So we start with them and end up with one. Now the problem here is, well, sort of drawn there again with strange and looking space, but it does happen. Oops. This is better. Okay. Look there. It's more important. Okay. So here you see those red and blue clusters, they are separated, correct? So we merge them because we use the metric, and at some point, we like the cluster, this cluster, this cluster and this cluster were close in terms of a metric, and we join them, right? And those blue ones and those dark blue ones as well, or indigo ones. Blue ones, indigo. We solved that. See, here it's solved, and we solved it with a connectivity constraint. A connectivity constraints, well, it's a constraint on the connectivity of clusters. What does it mean? We select some threshold, some constant, epsilon, for example. And we only connect clusters if the minimum distance between clusters is less than epsilon, right? So we now, instead of maximum, we calculate minimum. So the minimum is here, this one. Here is something like this. And like this. This minimum is like this. So we only connect clusters if they are connected. The minimum distance is lower than the threshold. And this solves the problem. But it can lead to a situation where we don't end up with one cluster. Right? At some point, we can end up where every cluster, every pair is distant from each other. Right? And we do not connect them because we have a connectivity constraint. But in a way, that's a good stopping point, is a good way to determine what is the correct number of clusters. Right? So if you introduce a connectivity constraint and you stop at 5 clusters, well, maybe 5 clusters is the correct. Here is a picture of comparing those 4 algorithms and agglomerative clustering with different metrics. Different sized clusters, different shaped, and this is the best situation, right? 3 clusters, very dense, very separated. We know the outcome, no point. What do we see? A mini batch k-means just means that we don't look at all points. Let's say we think that they're evenly distributed and we take some subsample of points and cluster them, and hopefully arrive at the same conclusion. And also there is the time of convergence. And k-means and dbscan are the fastest ones. Agglomerated clustering is the slowest one because it goes through calculation of fairways distances many times. Okay, what is your favorite one? Well, yeah, here it's good. First of all, because everything is dense. dbscan is density based. So if all clusters are dense, then dbscan is the algorithm of choice. And it works fast, and there are anomalies here. See the block point here, and I think over there as well, one black point. Here, like k means, well, you have to predetermine the number of clusters. Right? So here is a good example: 3 clusters. Actually, 3 clusters, but k means says it's 2 because we told it that it's 2 clusters. Min shift does not need the number of clusters to be determined, but determine that there are 3 clusters here, 1 cluster here, 2 clusters here, but see, again, because it still separates into Werner diagrams, right, with oddly shaped clusters, not so good. Agglomerative clustering, again, outputs you a variety of numbers, right, so you have 3 clusters, 4 clusters, 2 clusters, whichever one you want, and here you just selected 2 clusters. And here as well, just a small cluster. Okay. So how do we select the best algorithm and the best parameters if we do not know what we want from the algorithm? Well, there are clustering metrics. And clustering metrics separate into external and internal. External metrics usually mean that we have some task after the clustering, and we probably have some labels. So let's say we want to generate some new features. That means that we have our points, and they're not only points in space, they also have classes assigned. Right, so now we have classes on axis, right? If we have labels, if we have classes, then we can use external metric. The best one is, of course, your end metric. End means what do you actually use to evaluate your algorithm that will go after clustering, right? If you have precision recall, you do some clustering, take features, then you calculate precision recall, and it's better, then the clustering is better as well, correct? If you don't change anything in the algorithm. So you fix the parameters of the algorithm, and you change clustering method, and then you find the best clustering for your task. This is the best way to determine how good is your clustering, because it directly connects to your quality. Then there are other stuff. Not so good, but still. So rank score aims at how often do pairs of points in one cluster belong to different labels or different classes. Mutual information, sort of the same, tells about how stochastic is your distribution within a class, within a cluster. And a homogeneity score is interesting. It calculates the number of points in the majority class in a cluster. So let's say we did clusters. Like this, like this, let's say like this, and like this. So a homogeneity score is, okay, how homogeneous are your clusters? So you calculate the number of points. So here, for example, 1, 2, 7 points out of 9. Here are 2 out of 2. Here again 2 out of 2. And here are 5, 5, 10 out of 12. So you calculate the number of points in every cluster that belong to the majority class, not to the biggest class. And then you just divide. So you add that up and divide by that. So and this is here. So here is you sum up the maximums and divide by the total number of points. Okay. Now this is easy because you have a label, but if you don't have the label, you have to think about geometry and how pretty are your clusters. But you need, a prettiness score. Because you can't look at how pretty your cluster is, especially in 100-dimensional space. So if you cannot look, you need a number, and the prettiness number most often used is the silhouette coefficient. You see, even the name, basically how pretty are your clusters? What is their silhouette? The silhouette coefficient is easily calculated. You have the mean distance between a sample and all points in the same cluster, not class, this is the typo. So in the same cluster, and this is A. And this is the mean distance between a sample and all points in the closest but other clusters. Right. So the point here, for example, here we calculate the A is the mean distance to all those points, right? And B is the closest distance to all those points. The mean distance. And you get a silhouette score for 1 point. And then you average them up over the whole day. And you get a number. And the higher or lower do we want our silhouette score to be? What is good? High silhouette or low silhouette? Any ideas? High, sure. So we want clusters to be as dense as possible, right? So we want A to be as low as possible, but we want them to be far apart, right? So we want clusters far away from each other, but dense within themselves. So we want B to be as high as possible, A to be as low as possible. So we want the silhouette coefficient to be as high as possible. Okay, some other not that often used but still useful variants are Dunn index. So the Dunn index is we take the minimum distance between cluster centers in this case, and divided it by the maximum distance within one cluster. Alright, so it's the biggest cluster, calculate its diameter here, and take the distance between. And this, do we want high or low? High or low? It's actually an easy question. There's no trick there. Yeah, that's high. We want clusters to be as dense as possible, right? As far away from each other as possible. But both those indices sort of take an approach of only taking, well, Dunn index is the most sort of shifted because it only looks at two variables, right? One minimum distance, one maximum distance. Silhouette looks at the closest clusters, which is better, but still it does not look at everything. Well, close to silhouette distance, a little bit more complicated, is the Davis-Baldwin index. And Davis-Baldwin index is this abomination here. Okay, so how do we calculate? We go through every cluster. So let's say the clusters like this. So let's say clusters are K. 1, 2, 3, 4. And for every cluster, we calculate this. So we calculate the distance within a cluster. So the average distance is that. Plus, so we calculate for every pair, right? So we calculate plus the distance within these clusters and divide by the distance between clusters. So we calculate for cluster 1, we calculate 1, 2, 1, 3, 1, 4, and then select the maximum. Right, so for every cluster we get the metric, and then we average it within all K clusters. You know the question, right?
Так, сейчас черпаем быстрее, что
Average. Average distance
все
between the point within a cluster to its center.
Окей.
So, what is the question and what is the answer? Okay, the question I tell you, do we want this high or low? Yes. It's not low. No, we want this as high as possible, and these as low as possible. So high, high, low. Oh no, no black. Okay. Any questions regarding cluster? Okay. So one thing we use clustering for is extraction, information extraction, another is feature generation, but there is actually one more application for clustering, and that's in the realm of semi-supervised learning and active learning. So let's say we have semi-supervised, this is just a reminder. So if we have 2 points, right, a separation is like this, but it may not be accurate if we have another gray unlabeled points, because it will give us more information. And we can employ clustering for that. So for example, we can first cluster, right? So how we can apply a clustering algorithm. So for example, here we apply agglomerated clustering of the scan or something else. And now there are 2 clusters, and we take the cluster and we assign all points the label the majority class. So let's say we only have those colored points, and we separate them in 2 or 3 clusters, and we say, okay, now all those points are green, all these points are red, and all these points are red as well.
У вас есть вопрос, зеленая точка, попавшая в тот, кто красный красным, тоже или красный?
Very good question.
Мы ее объявляем выбросом, мы красным или красным?
No. We leave it as this. We leave it as green. So all these will be red, but this is still green. Why? Because we probably spend some money to know if it's green or red, and we don't want to throw it away because of clustering.
А может, вы потратили деньги, потому что поняли, что она будет сразу не стоит ее выбросить, когда...
Probably not. It's actually a much deeper question than you think. It goes to the how do you know if you fine-tuned your data too much? Let's talk about it in the because this is a very, very important topic, but we'll go maybe. But for now, these are red, these are red, these are green. And this is where agglomerative clustering is actually very good, right? Because you say, okay, if there are 2 clusters, then these points in this big cluster, there are 4 red and 4 green, and we don't actually know the class. So we go down in hierarchy, right? These are separated, and now these are mostly red, these are mostly green. So we take all those green, all those red, except this one, and all those red, and apply an algorithm. For example, KNN. Semi-supervised learning can use clustering. If you go into active learning, so you can again use the same principle, right? So as a reminder, active learning is when you have a budget and you can ask a human or something smarter about these points, right? Whether they're green or blue, right? Or green or red. So first, and a good thing again is use hierarchical clustering, because you do agglomerative clustering once, you arrive at the structure of your data. So you have 2 clusters, they go to 3 clusters, and each step is separation of the cluster, right? So even if we change the sequence of steps, right, we still get the hierarchy. So let's say we go down a number of clusters, and your agglomerative clustering actually merged these 2 clusters. So let's say there are 2 clusters here, and they were merged before these 2 or after, right? So let's say the previous step, so this step is with 2 clusters, and previous step was with here is a 1 and here 2, right? But it does not matter because for every cluster was merged, right? So even if the sequence is not the same, this big cluster was still merged from 2 other clusters. Because that's the only way in agglomerative clustering that you get a cluster, by merging 2 clusters, right? So you can say, okay, we left this as this because maybe it was merged earlier or later, but it does not matter. This cluster still has a hierarchy within itself because it was merged, so there's still a tree of mergers. So what we do is we take our data, create a hierarchical clustering, then go step by step and say, okay, 2 clusters. Let's just sample, here we sample, for some reason, 6 points here and 8 points here. But it should be the same, right? I think it's just a representation. So say, okay, we take 10 random points from this cluster and 10 random points from this cluster. Right? Or a number of points that will give us the good statistical assurance. So we take 10 points here, 10 points here, and we ask a person to label them. Or launch a model or something else. Say, okay, all points from this cluster were red, and there are some red and some green. So we go down into hierarchy, right, and we resample. So now we have 5 here, 3 here. It's okay, let's take additional 7 here, additional 6 here. And then again, if those are all green, we leave it as this. If there are some still red, some green, we go down in hierarchy again. A way to do active learning. Now, the more common way, if we don't want to do clustering, but still want to do active learning, is what is called a label propagation. And label propagation still relies on distances between points. So you need distance, but it works on a graph. So the first step is you build a neighborhood graph. Done. So a neighborhood graph is you connect points where the distance is lower than some threshold. So you select the threshold, if the distance is lower, you connect the points. Neighborhood graph. Then you query. Query means you ask a person, right? You query a person or some other thing. Label some random points. And say, okay, this is a blue point, this is a red point. Okay? And we know, ideally we know, sometimes there can be errors, but again, we trust the labelers or assessors. So, ideally we know that the probability of this point being blue is 1, because we know, and the probability of this point being red is also 1, because we know. I mean, probability of this thing being red is 0, and this blue is also 0. And then we propagate those labels. So every time we take a step, we lower the probability. And here we just subtract. So take 1. And actually for every point we have 2 labels, a blue one and a red one. So here is 1, 0, or 0, 1, there's 1, 0, but for simplicity I only take the highest number. Right? So we propagate the label, right? So we have, okay, this 0.8, this is 0.6, this is 0.4, 0.4, 0.6, 0.6. Right? You propagate your label. So for some points you probably know, okay, this is probably a blue point. This is probably a red point. But for some you don't. Right? Like we really don't know which point is this. Right? And we really don't know which one it is. And then we label some other point. Which one? Well, here it's this. Why not this?
Первую у нас она, вероятно, не такая.
Not which.
Ну ладно, короче. Видимо, у нас есть какой-то школ на то, что мы считаем, что если точка, это вероятность точка такая, и если точка попадает в школу по одному или другому глазу, тогда мы ее просим.
It's a good way. Yeah, I like it, but I mean, this is even less information, right? Well, the threshold is lower than something to take that way. Why is this point and not this one? Any other ideas?
Но она больше информации даст, типа она даст.
Because this point will give us more information about all the other points. It's more connected, right? But now we arrive at the problem of selection. Well, in this example, it's easy, right? We just have one point that is very good connected. We have 2 points sort of with the same uncertainty, but one of them is better connected than the other. Well, let's take this one. But what if we have a million points, a million labels, and 10 million connections, for example, right? How do we find the best points? And we actually arrive at the question of how do we select a point which is good on 2 metrics. Right? Let's say we have a point. 1, 2, 3, 4. And first metric is how low the highest number is, right? For example. Right, so here we say okay, this is number 1, this is 0.8, 0.6, 0.4. So the lower is the better, right? The lower the number, the more do we want to label this point, right? And then we take connections. So the next one, okay, this is 3 connections, this is 5 connections, this is 7 connections, and this is 4 connections. And let's say the list goes on, right? And this list goes on. But how do we choose now? 1 point. What is the best 1 point?
Способ
Name one.
Ну, мы можем отскейлить идеи и потом взять там среднее, прикольное среднее.
Yes, that's a good idea, but you have to think about how do you scale it. Like, let's say this is on one scale, but they are like distributed like this, and this is if we normally they will be distributed like this. Do you really want to average them, right? Or like even a worse thing, like this. But what is another idea of your dealing?
Хорошо, ну... Ну, надо же хорошую выбрать.
Sure.
Ну, если у нас есть какая-то информация по старым точкам, можно просто на них попытаться там KNN запустить и на этом уже выбирать, потому как.
Ну,
Well, it's sort of, well, label propagation sort of simulates already what you're trying to do, right? Because if you launch KNN, then for these we know, for these we don't. So this is already happened. So.
ну, если у нас граф не очень большой, хотя там на самом деле зачем, наверное, тоже отчасти может работать, мы можем по-другому смотреть. Если вот для точки мы пометим, ну, как бы подумаем про точку, которую мы еще не пометили, что будет, если мы пометим ее классом 1, посмотрим, как распространится этот класс, и как много нового мы еще узнаем, то же самое для класса 2, и
Very nice.
если, типа, там, мы много узнаем, даже если...
Sure. Sure. That's actually a very good idea. It requires some calculation, but this is probably the best way. Right? That simulate that we label that point and how much information we actually get from it. I like it very much. Okay, the easiest, a third way, let's say. Right? Because all ways are good if you can use them. The third way, which is actually can be used in many applications, when you have ordered lists on different scales and you want to select the best point, like you can just use rank, right? So for example, here you can say, okay, so this is the best, this is rank 1, this is 2, this is 3, this is 4, and here this is the best, 1, 2, 3, 4. And then you can just sum up ranks, right, and select the best one. So it removes the problem of scale. It adds some other problems, of course, right? Because it tends to select like mediocre points. Sometimes not. Okay, now this is the end for today in terms of lecture, but we will go to the question that was postulated previously. Any questions regarding the lecture, clustering or active learning? Okay.
Нет, у меня есть вопрос. Как мы дальше будем продвигать эти, ну, короче, вот мы сделали вот то, что на картинках нарисовано.
Yeah.
И потом...
Now we label this one
Да.
and launch it again. So we propagate the labels again.
Ну, то есть не до конца понятно, как мы явно вот пропагейт делаем. То есть здесь мы берем просто, вычитаем 0,2 из того, что у нас есть.
Yes. You can do the same thing again.
Перекрывает то, что у нас старое
Yes,
было?
yes.
Окей.
So this is new. Now, for example, let's say this is red point, right? And we propagate labels. So this goes from 0.6 to 0.8.6.
Да.
And this goes from 0.4.4 to 0.8.4.
Да, но вот, например, как это правильно сказать? Ну, то есть, если вот мы пойдем на... У нас там... Ну, то есть, если у нас там было раньше 0,8 на красную, а сейчас должно быть стать 0,6 на красную, то мы ставим 0,8?
Well, it can only go up, right?
Окей, все.
Because you only can add points.
Окей.
Okay. Now, даже не знаю, по-русски или по-английски. Это очень важная вещь такая, на которую лекция не ходит, но в целом машинное обучение ходит. Давайте по-русски. Про посмотреть данные и изменить данные. Вот хороший пример. Да, вот мы такие, о, здесь зеленая точка, она на самом деле красная. Давайте поменяем. Проблема в том, что вы как человек внесли свой байс любви к красоте, да, в этом смысле. То есть вот вы сказали, я хочу, чтобы вот чтобы здесь красненький был. Но у вас нет обоснования, что так считать вообще в целом. Да? И эта проблема, она часто случается, когда вы начинаете особенно анализ данных, а проблема интегрирования данных. Да, и там под настройки вашего алгоритма. В чем проблема? В том, что если вы заточите ваш датасет для того, чтобы у вас хорошо работал на этом датасете, возможно случится так, что когда у вас реальные данные пойдут, все поломается. И более того, это случается. Прям случается. Но тут есть проблемы, связанные с последними достижениями в науке и технике. Есть такой термин, называется data-centric машинное. Недавно появился, год-два назад, который говорит о том, что не надо искать очень хорошую модель, надо данные лучше подобрать. Модели, немножко противовес идет. И это очень важно понимать, на самом деле, что нет, не идет противовес. Потому что важно, чтобы подбор этих данных осуществлялся тоже алгоритмом автоматически. Да, то есть вы определяете метрики, определяете принципы, по которым данные определяются, и потом запускаете его. То есть вы не смотрите, как человек, я хочу красненькую точку школы. Да, потому что человек он на самом деле может очень много байсов вносить в машинное обучение из-за любви к красоте в основном. То есть мы хотим, чтобы были цифры побольше, значит, кластеры покрасивее и так далее. Из-за этого человек начинает лезть в алгоритмы и вносить свой байс. Вот прям так называется Introduction of Human Bias into a System. И это проблема, потому что человек не идеально существует далеко, да. Я выступал в МФТИ, лекцию читал про промышленный искусственный интеллект. Меня там студенты спросили, в какой момент вообще можно доверять искусственному интеллекту? В тот момент, когда метрики нормальные. Типа искусственный интеллект ошибается реже, чем человек, то можно доверять. Как мы людям доверяем, а искусственному интеллекту нет. Я говорю, это потому что вообще, я говорю, многим людям вы доверяете, если по-честному. Да? Готовы ли просто человек встретиться на улице и доверить ему что-нибудь? Наверное, нет. Да? То есть, потому что, в принципе, знаете, уже знаете, что человек очень сильно такое существо с байсом. У каждого свое смещение видения картины мира. Это плохо. Когда это вносится в алгоритм обучения, это прям часто происходит. И об этом надо помнить. Окей, на этом все. Спасибо, Олег ушел. 10 минут перерыв, да? 2:30 тогда.